The broadcast is now starting. All attendees are in listen-only mode.
Okay, it's 7:30, so why don't we begin the presentation? As you can see, I'm going to have all of your microphones muted. So if you have questions, you can raise your hand, and Martin will be typing in answers to your typed in questions. And if you prefer, you can hold your questions till afterwards and just send us an email at staties.com. So my name is Pat Whitcomb, and I'll be presenting tonight. So to ask a question, if you just press the raise hand button so that I know that you can all hear me. Okay, I see 1, 2. Okay, it looks like you can hear me, so I'll continue with the webinar. So what I'm going to do is talk about building designs when you have an irregular space that you're trying to study in. And I'll be talking about two types of constraints that are often needed. The first is linear constraints that form a convex space. And then I'll talk about nonlinear constraints and or linear constraints that form a concave space. So the problem we're trying to address is when you design experiments and you input the high and the low value for each of the factors, that defines a cube. And there may be regions within that cube that should be excluded from the experimental space. And so how do we approach this? Well, the first question you can ask are the constraints linear or nonlinear? And then the second question is the experimental space concave or convex? And then that'll tell you what type of constraints you need. So first I'm going to demonstrate linear constraints that form a convex space. This is the easier case. Then I'll demonstrate linear constraints that form a concave space and nonlinear constraints. These both use the same technique, and it's somewhat more involved, but as long as you follow the steps, it's not too difficult. So to illustrate this problem, I'm going to use a simple example of making corn pudding. So the problem we're trying to address is that when we have just upper and lower bounds on the individual factors, they define a cuboidal space, and additional constraints may be needed if some of the points within that space would result in failures or are possibly impossible to run. So a linear constraint is just like the name involves. Instead of having a low value and a high value on a single factor, which is where we start, we have a low value and a high value on a linear combination of the factors, where these coefficients are scalars, and we have a linear equation involving some or all of the inputs. So let's look at making corn pudding. So I'm using this example because I love corn pudding, and so I wanted to run an experiment to see if there was a better operating conditions, a better time and temperature to get the texture I wanted. And so I wanted to vary the time from 60 minutes to 90 minutes, and I wanted to vary the temperature from 325 to 400 degrees Fahrenheit. Now, the problem with this is I know that if I use the highest temperature, 400 degrees, for the longest time, 90 minutes, it's going to be burnt. So my choices are either to reduce the space, so see the picture of the corn pudding, I could reduce the range of time and reduce the range of temperature, and I could operate in that smaller space, But you can see that leaves a lot of the space that might have interesting texture unexplored. So what would be better would be to eliminate that corner where the time and the temperature is too high. So what we do is the steps we go through is first we identify the corner of the space that we want to exclude. So in this case, the corner we want to exclude is the longest temperature, the longest time and the highest temperature. So we want to eliminate the vertex where A is 90 and B is 400. The way we do that is we say, okay, if we're going to use a temperature of 400, what's the longest time I can have the corn pudding in the oven? And we said, well, if we're going to use 400, the longest time in the oven is only 60 minutes. So that comes our constraint point on time when we're at the high temperature. Then I say, if I'm at the longest time, what's the highest temperature I can use? And we say, well, if we're going to be in the oven for 90 minutes, the highest temperature we can use is 350 degrees. So that becomes my constraint on temperature. Now, those 2 points define a line, and that's our linear constraint. So we always want the time to be less than that line and the temperature to be less than that line. So we want to be to the left and below that line in all of our experiments. So what we're going to use is an optimal design because this isn't a cube and none of the standard designs fit. And we have 2 factors, time and temperature. And the time goes from 60 to 90 minutes. The temperature goes from 325 to 400 degrees Fahrenheit. And now we're going to add a constraint. So we click on the Edit Constraints button that's at the bottom of this screen. I'm not showing it. And that brings up this box. And if we knew the linear constraint, we could just type it in here. In this case, we know what vertice we want to eliminate, and we know what factor levels we need to eliminate it. So I click on the Add Constraint tool. That then brings up this box. And so we've got our time, its range, our temperature, its range, and we define which one of the vertices we want to eliminate. In this case, we want to eliminate the highest time and the highest temperature. So the 90-400 vertex. So then we go in here and we say, okay, when the temperature is 400, what's the longest time we can use? Remember we said when the temperature was 400, the longest time we could use was 60 minutes. So we put that in for our constraint point. Then we go to constrain when we say we're at 90 minutes, what's the highest temperature we could use? And we said at 90 minutes, the highest temperature we can use is 350. Now defining those 2 points then and solving gives us this linear constraint. So Design Expert just does a little bit of algebra and out comes the linear constraint. We then click the OK button and we click Finish, and that'll build a optimal design for us. And if we look at this design using the design evaluation tool and we look at the contour, we can see we're getting that linear constraint cutting off that vertex of 90 minutes and 400 degrees and keeping all the runs in the space where we expect to get not necessarily good corn pudding, but at least corn pudding that's recognizable. It's not burnt to a crisp. So let's apply this to an industrial example. So we're going to look at an exercise where we're going to study an extruder. And so in this case, we have engineers that are working on an extruder, and they're trying to find conditions that maximize the flex modulus of the material we're extruding. So the conditions you extrude under add work to the material you're extruding, and that's going to affect the flex modulus or the stiffness of the material. And we want to find the right combination of screw speed and throughput to get the flex modulus we'd like. So for this optimization, they want to define a response surface experiment that can predict the mean response or the mean flex modulus within plus or minus 4 units. So some considerations is the flex modulus is going to be a function of the work, which is a function of the screw speed and the throughput. And the throughput is actually going to be dependent on the screw speed. The higher the screw speed, the more material we can put through the extruder. If we put too much material through at too low of a revolution, that builds up torque on the screw. And if we're lucky, we'll blow the seals. If we're unlucky, we can actually warp the screw. So this is where the multilinear constraints will come into play. So the screw speed we want to study is going to vary from 300 to 500 RPM. And the material we're going to push through, or the throughput in pounds per hour, is going to vary from 600 to 1400. Now, we don't want to have a problem with the extruder, so we don't want to exceed the torque limits. So a higher throughput is only possible at higher screw speeds. So we have to translate these torque limits into a multilinear constraint. So the extruder manufacturer provides the specifications, and we decide we're only going to go up to 95% of what the manufacturer gives as the allowable maximum. And so we do some range finding experiments, and we find that at 300 RPM, we can go up to but can't go beyond 800 pounds. And so we just start at 300 and keep increasing the throughput till we get to 95%. We find out that's 800 pounds. Then we run it at 500 RPM and 1400 pounds per hour. And then we start decreasing the screw speed till we hit 95% of the torque limit. And that occurs at 450 RPM. Okay, so now we have our linear constraint that looks like this. The vertex we want to eliminate is the low screw speed and high throughput, because that's going to be too high of a torque. So we now know that if we're going to run at 300 RPM, the maximum throughput we can have is 800 pounds per hour. And if we're going to run at 1400 pounds per hour, the minimum screw speed we can have is 450. All right, so we want A to always be greater than the value on this line, and the throughput, or B, to always be less than the value on this line. Then we're in the region where we can experiment and know that we're staying within 95% or less of the maximum torque. So we go through our planning process. What we want to do is increase the flexural modulus of the material we're running through the extruder, and define what precision we need. We want to be able to predict this flex modulus plus or minus 4 units. So we're going to use our D. The precision that we want is to be able to predict the mean flex modulus plus or minus 4 units. And then we need an estimate of the experimental error. Well, we've made similar materials in the past, so from historical data, we know that if we do these experiments, we expect the error. So if you think of the standard deviation at the bottom of the analysis of variance, the unexplained error in the experiment, we expect that to be about 3.7 units. Okay, then we pick our DOE space, 300 to 500, 600 to 1400. We want to never exceed 95% of the allowable torque. We did our range finding. We found out what that involves. Okay, we're going to design for a quadratic model. We're going to use an I-optimal design with multilinear constraints. We're then going to use the D, the plus or minus 4, so D is equal to 4, and the S, the 3.7, and the fraction of design space graph to make sure we have enough experiments to achieve the precision we want. And then, of course, the last step in any design is after you have your design, you want to go through and mentally run each one of the combinations and think about whether it's doable, safe, and will result in meaningful data. Okay, so we select an optimal design for 2 factors, and we input the levels. We then click on the Edit Constraint button. Okay, this time the vertex we want to eliminate was the 300, 1400, and we have 450 and 800 as our constraint points. So we go in there and we say when the throughput is at 1400, the RPM has to be equal to or greater than 400 RPM. When the RPM is 300, the throughput has to be less than or equal to 800 pounds. That then results in this linear constraint. We click OK and next. We build our design. So we have 6 model points, 5 lack of fit points, 5 replicates. That should give us a decent response surface design. We then go in and look at the fraction of design space plot, putting in the D equal 4 and the S equal 3.7. So there's our 4, there's our 3.7, and what we see that is in this design space, 56% of the design space will give us a precision of plus or minus 4. So that's a confidence interval on the predicted mean of plus or minus 4. And the other 44% is going to give us a plus or minus greater than 4. Okay, so if we look at that, since this is two-dimensional, we can see it. What that's saying is this line, which occurs at 4.85, that's the standard error that we can tolerate and get exactly plus or minus 4 for our precision. So when we look at a contour plot and we draw that plot, it's saying within this red line, we're going to have the precision we want. We'll be able to predict the flex modulus plus or minus 4 or better. Outside of this red line, so this 44%, we're not going to have enough precision. Now, typically we'd want to have about 80%, and so we'd like to have greater precision than we're achieving with this design. So what we're going to do is we're going to rebuild the design, and we're going to add some additional model points. Okay, that will give us a larger sample size and improve our precision. So we're going to add, in this case, 3 additional model points. So now we have, instead of having 16 runs, we have 19 runs. We rebuild the design. Now when we look at the FDS graph, we need to have a standard error of 0.5 or smaller to get the precision we want. That goes up a little bit because we have a larger sample size. The T value gets a little bit smaller for that confidence interval, so we can have a slightly larger standard error and still achieve our precision. And it turns out that we're right. That gets us right at 80% of the design space. So now if I look at that design, here's my red contour. 80% of the area that we're studying, we're going to have precision of plus or minus 4 or better, and then this other 20% outside that red contour, we're going to have precision somewhat less than that. Okay, so this is just an aside. That's why it has the statistical detail. If any of you are familiar with power, power doesn't work once you start putting in constraints, because power is your ability to detect individual coefficients, and constraint causes collinearity or correlation among the model coefficients. So you can see that even though we've got the precision that we need, the power for most of the coefficients is quite low. And no matter how many runs you add, you still have the collinearity and the power will always be low. So if you want to learn more, excuse me. If you want to learn more about how to use fraction of design space to size your DOEs, we did a webinar on that in the past, and you can find that on our web page, and here's the link. or just go to our webpage and search for webinars and look for the webinar on sizing, mixture, and RSM designs for adequate precision via factor of design space. Okay, I'm going to just quickly show some more examples. I'm not going to work through them, but just to give you an idea of how you can use linear constraints. So here's a three-dimensional example. It's the same thing. We pick the vertex we want to eliminate, and we just pick constraint points. And we say when the vertex we want to eliminate, in this case, is the high A, the high B, and the low C. So we just say when B and C are at their vertex values, what's the highest value of A I can use? And I have to back off along that edge of the cube to 1350. Then you say when A and C are at their vertex values, how far do I have to back B off? And I have to back off down to 200. So I think a run of 1700, 200.2 will work. Then I say when A and B are at their values, how much do I have to increase C before I can get it to work? So when A is 1700 and B is 225, I think I have to increase C to 0.45 from the 0.2 to get it to work. Okay, and you can see this could go to any number of dimensions. You just look at the combination and decide how far you have to back off each factor one at a time along the edge of the hypercube away from that vertex. Then Design Expert will calculate the constraint for you. You don't have to have all the factors involved in a constraint. So you can see in this case, what we're doing is we're going to skip factor B. So rather than cutting off a vertex, we're eliminating that side of the cube. Okay, so it's possible to say, okay, this factor is not involved in the constraint. Okay, and that will calculate a constraint. And you could cut off, extend out beyond the cube, so you're not just cutting off the corner, but cutting off a geometric portion of the cube. Okay, so those are just some exercises that you can have available and work through on your own. Okay, so now for the more, well, for me, the more interesting part, although I'll have to say I use linear constraints a lot more than I use nonlinear constraints, and more design spaces are convex rather than concave. Maybe that's why these are more interesting, because they don't get used as much. So we're going to talk about linear constraints that form a convex rather than a concave space. Then we're going to talk about nonlinear constraints. Okay, so the way you handle a design space there, you have linear constraints that are going to form a concave space, is you start out building a design that covers the unconstrained region. So we're going to use a user-defined design, and we're going to put in lots and lots of discrete points. This design will then form the basis for a candidate set that we're going to use for the constraint design. You must include each constraint that you have in an indicator function. You can have several constraints in one indicator function, or you could have several different indicator functions. Then we're going to use the response simulation to construct the indicator functions. So each constraint is going to be entered in a response column as an indicator function using the use as equation and analysis. And it's going to be put in as an if-then-else statement. We're going to assign each point in the starting design is going to be assigned a value greater than 0. In this case, we're going to use a 1 if that point's in an acceptable region, and we're going to assign it a value of 0 if it's in an unacceptable region. Then what we do is we sort that design by the indicator function. We delete all the rows where the values are 0. So those are all the runs we can't make. We then save the remaining runs. All these runs are acceptable. We use that as a candidate set. So we use design tools, write candidate set. Then we're going to build our design as an optimal design But now we're going to use point exchange, and we're only going to select points from that candidate set we just created because we know all those runs can be made. After building the design, we're going to re-enter the constraint indicator function. Then we're going to run that design, analyze it, and I'll show you how you can optimize and stay away from the constrained regions. Okay, so we run the DOE, measure the real responses. Oh, one last step, and this is just to get around a little problem that Design Expert has. If we eliminated all the runs that were 0 and all we had left were runs that were 1, when we went to the optimization, it wouldn't allow us to optimize on that response because it would only have a single value. There's nothing to optimize. So we have to create one run that has an indicator value of 0. And of course, we won't run that because it's in the unacceptable region. But that'll allow us to restrict the optimization to non-zero values. So we'll see how that works. Okay, so linear constraints forming a convex space. So first we build our user-defined design, and this design is going to form the basis for the candidate set. So we want to build a grid of points, and we want to have quite a few points. So I'm going to study A, which is going to vary from 10 to 20. I'm going to put in 51 levels. And I'm going to study B that varies from 20 to 30, and I'm going to put in 51 levels. So that's going to give us 51 times 51 candidate points. So we're starting out with a grid with 2,601 points, just the product of those two. And wherever these lines, each corner of these cubes are a run. Now the constraints I want to have are like this. So I want to cut off the corner that's high. Now I add a constraint that goes from the point that's A14 and B30 down to A16, B26. Then I want to have another constraint that goes from that point over to this point that's 2024. Now you could see if I used the regular linear constraints, I'd have a constraint that goes across and cuts off a lot of the design space that I want to explore because this is concave rather than convex. So we're going to have to figure out how to get around that problem. Okay, now we can't use the constraints tool for this because it would draw those lines all the way across the square. So what we have to do is we have to figure out what the constraints are. Okay, so for any n-dimensional design, n non-singular points can be used to define a plane passing through the space. Okay, so if I look back here, to define, this is two-dimensional, so to define a line I need 2 points. So these 2 points will define a line, and these 2 points will define a line. Okay, so for a process design with k non-singular points. Note selecting k points on the edges of the hypercube always produces a non-singular set of points. Okay, then we calculate the equation. So we have to actually go in and calculate that linear constraint on our own. And we'll see how to do that. So we know the points, right? For A, we've got 1430 and 1626. And for B, we've got 1626, this point in the middle, and then 2024, this point over here on the edge. So at this point, I could go into Design Expert and put that data in. So A is here, and then my response, I'm going to put in the values for constraint 1. So there's point 1, 1430. And there's point 2, 1626. Okay, I can just go down here and analyze that and fit it with a linear model. Go to the ANOVA. Now I want to look at the actual equation, and that's my constraint. So the constraint I have for A is this. Constraint 1 equals 58 minus 2 times A. Okay, so 58 minus 2 times A. I just solve that then. B's equal to 58 minus 2A. Solve that to make it a linear constraint. I carry the 2A over to this side, so I've got B plus 2A is greater than 58. Now I can do the same thing for constraint 2. I've got the point 1626 and 2024. Okay. So I've got that data in here, 1626 and 2024. I analyze that, fit it with a linear model, go down here, get the actual equation. So B is equal to 34 minus 0.5A. B is equal to 34 minus 0.5A. Solve that, I get a linear constraint. So what I want to do is I want to exclude points where these two constraints are both met simultaneously. Okay? So that will then include all these points that would be excluded if I did just one constraint at a time. So I'm going to force it to do both constraints simultaneously. Okay, so I just set up a constraint function. Okay, so I can go do that. So there's my candidate set, that grid of points that I built with the user-defined design. I go to simulate, equation only, and I put in there those two equations. If B plus 2A is less than or equal to 58, it's a 1. If it's not, it's a 0. Plus, if B plus 0.5A is less than or equal to 34, it's a 1. If not, it's a 0. Okay, that'll then create runs where both of those conditions are met, where it's a 2, where only one is met, where it's a 1, or where they both fail. And that's the ones I want, where it's a 0. Okay, then I can just sort this, delete all the rows where it's 0, and then form a candidate set that will only have runs that meet both of those constraints. Okay, so I eliminate all those points, delete the rows where it's 0, save the remaining runs, use that as a candidate set to build my new design. Build my design as an optimal design using point exchange. And then I re-enter my function. Okay, so if I go over here, I re-enter this function then into my final design. I put in one run where it's going to be a 0. Okay, of course there's no response value for that. Okay, now when I go to analyze it, I can say, because I put this 0 in, it's got one run where it's a 0, I can say I'm gonna restrict my run, my optimization, to only search where that constraint function is 1 or 2. In this case, greater than or equal to 1. Then let's say I want to maximize the response. So let's say I had some data and I analyzed it. So when I go in here, I'm going to try and optimize it. It finds the function, the value of A, the value of B, the value of Y, but it doesn't go into the region where I have zeros. So that looks like this. Here's my desirability function. So you can see the blue is the 0 where I'm not meeting either constraint. Or it's a little bit easier to see in the constraint function. So the blue is the 0 where I'm not meeting either constraint. The green is the 1 where I'm failing one constraint or the other, but not both. And then the red is the 2s where I'm meeting both constraints. So you can see then when I do the optimization, the function optimum is here, but it stops when it hits that constraint because we're now extrapolating into a region where we can't run. Okay, we can't run in that blue region. And because I have that constraint function in the optimization, it knows to stop when it reaches that point. Now, nonlinear constraints are pretty much the same thing with just a different constraint function. So I start again by building my user-defined design. So again, I'll use A from 10 to 20 and B from 20 to 30. This time what I want to do is I want to eliminate the runs inside this blue circle. Okay, so I just set up a constraint function that has the radius of this circle, the coordinates of the center of the circle, okay, and where this is greater than the radius squared, this function is going to be 1. If it's less than that, so it'll be inside the perimeter of that circle, I'm going to give it a 0. So all these runs in here, inside the circle, are going to be 0s. All these runs outside are going to be 1s. So again, I set up my indicator function. So I can go in here and just set up a blank response, put in that equation for the perimeter of a circle, and assign it a 1 when it's greater than the radius squared, and a 0 when it's less than the radius squared. Sort this. Go through and delete all the rows where it's 0. So I delete all those rows, and I can write this as a candidate set, and I can build a new design. Except now I'm going to do an optimal design. And now I'm going to use point exchange, and I'm going to read in this list I just created. And I can build my optimal design with only runs that work. Okay, I don't want to take the time to type in the constraint function, but I'd then enter that constraint function. I'd put in an additional run where I get a 0. So I just put in the center of the circle where I get a 0. Run that design, get the data. Again, I can now constrain this to be to only search in the region where we have met the constraint. I can then optimize it, get the results, and you can see here again, there's my 0s are the blue, the reds are my 1s. I tell it to optimize, and again, the extrapolation of the function would bring it somewhere to the midpoint of A, but because of my constraint function, it stops when it hits the 0 point. Okay, so that's my presentation. I hope you're not disappointed that it didn't take the whole hour, but hopefully you got something out of this. I know it's probably a lot to absorb in a short period of time, but you can go download this presentation from our website, and this is where you can also find the presentation on sizing designs with the fraction of design space. I haven't been paying any attention since I've been presenting. Hopefully Martin's been answering your questions if you've been asking them. If not, that's not a problem. Just send your questions to stathelp@statease.com. And thank you for attending, but I have one more slide. So a little advertising for Staddies. We're going to be co-sponsoring an analytic solutions conference with a Norwegian company called Camo that makes software for multivariate analysis, but we're handling the DOE track in that conference. And it'll be this summer. And it'll be June 18th to 20th in Minneapolis. We got really happy to get a couple of really high-profile people for keynote speakers. Jeff Vining from Virginia Tech, who's a well-known expert in design of experiments, and Dennis Cook from the University of Minnesota. So if you're familiar with Cook's distance, you're familiar with some of Dennis Cook's work. And so if you're interested in attending this conference, again, you can find details on our website. And I hope you got something out of this. So with that, I'm going to end the conference, and I thank you all for attending. I hope it was worth your time.